Okay, this is 2008 question 2. Again, it's another kinetics problem. Um, for the gas phase reaction listed above, the following data were obtained. You're going to notice on this one, they are introducing this idea of experimental error. So I'm going to do colors again. So to find the order of A, you find a set of trials in which B doesn't change or doesn't change much. So here there's no change. Well, there's a little tiny change. Here, if you do 0.0136 divided by 0.034, you will get, this is a 4, so 0.034 times 4 is 0.036. If over here you do 1.07 times 10 to the negative 2 divided by 1.08 times 10 to the negative 2 and do it on your calculator, these cancels. This is really darn close to 1. And so now this is an interesting question. 4, so you made A 4 times more concentrated, you left B alone, and the reaction rate didn't change. It stayed the same. The ratio is 1. And so the question is, 4 to what power gives you 1? Well, 4 to the 0 power equals 1. So this stuff, if you come down here, sorry, I kind of jumped the gun. A is determine the order of the reaction with respect to A. I'll put that on the next page. But it's 0 order. I'm going to grab a different color pen. Let's do purple. To find the order of B, you leave A alone, which looks to me like this is as close to not changing as this can be. This also goes up by a factor of 4 because 0.0136 and 0.0137 are essentially the same. And this, believe it or not, if you get out a calculator, 1.08 times 10 to the negative 2 divided by 6.67 times 10 to the negative 4. And that's just something I would do on a calculator. And this ends up being 16. That this number is times 16 is this number. So 4 to what power gives you 16? This is a 2. And so if I go, and so again, you just analyze that. What is the order of the reaction with respect to A? It's 0th order, and I hate that terminology, but that's the terminology they use. So 0th order. When it says justify your answer, I think the table does that, but if you're taking the AP exam, you might want to go back and say something along the order. Look at the blue. In experiment 2 and 3, the concentration of A quadrupled, the concentration of B remained constant, and the rate didn't change. So A doesn't affect the rate. That's what 0 order means. Something on that order. So something like in experiments 2 and 3, the concentration of A quadrupled and the concentration of B remained essentially constant, and the reaction rate did not change. Hence, I like how I spelled hence there. Hence, 0th order with respect to the concentration of A. Kind of the same thing down here, but I'm going to have to do this, and I'm going to have to extend the page. when I get there. So what happens in what's the order with respect to B? In this case, I would say it's second order with respect to the concentration of B, and the reason is in experiments 1 and 2. So let me just do this because that's A, this is B. The concentration of A remained essentially constant, and the concentration of B and the concentration, or I should say, of B I don't know, it's hard with those brackets, quadrupled, and the rate increased by a factor of 16. Hence, second order with respect to B. Just give them something so that they know that you know what you're talking about and you didn't just guess. And so this is what we know so far. We know that the rate is K, and then the concentration of A the concentration of A is the 0th part, and they really want you to do this on the AP exam. They want you to put the 0th order in there so that they know that you checked it. Then you can do anything to the 0 power is 1, and I think for this one, this is fine. I'm just going to do a little quick review here. The rate law always has this constant, which is like the slope of the line, and then it only has the reactants in it, only the reactants. And if you have a reactant that's 0 order, that means that that reactant does not affect the rate. Now, putting all kinetics together, I don't know when you're doing this problem, but when you have a reactant that doesn't affect the rate, it's because it comes in the reaction mechanism after the slowest step, because the slowest step determines the rate law. So A must be in the reaction mechanism in a step after the slowest step. Determine the rate constant and make sure you show units. So just going back to our answer for the previous slide, if the rate is equal to K times the concentration of B squared, well then if you want to solve for K, you take the rate for any trial, I always use trial 1, and you divide by the concentration of B squared, because that's just basic 9th grade algebra. I mean, anything you do to the right, you have to do to the left. Then I would go get the rate. My sheet is showing 6.67 times 10 to the negative 4, sorry, this is a 10, molarity per second. Okay, and this is a particular bias of me. See this 2 here? Instead of putting the rate of B squared, I'm going to write it down twice, because I find over the course of my teaching career, and of course it's a reciprocal because it's downstairs, if I square it, people will square the 0.034, but they'll forget to square the m, or they'll square the m and forget to square down the 0.034. But just remember, whenever something's squared, it means it gets multiplied by itself. And so this cancels this. And the first thing that you'll see is that there's no unit on the top. This canceled. And then the bottom has m times s. And if I put 6.67 EE negative 4, so 6.67 E negative 4 divided by 0.034 squared, you will get, I have my sheet here, point, and we're going to keep 3 sig figs. So we are going to get 0.577. So that's K. All right, and that's enough work. They just want you to just show you work. I calculate the initial rate for experiment 4, so I'm going to go back here very quickly just because. So what happens is we now know the rate law. So what they want us to do is they want us to put in this concentration for A, which is 0th order. I'm probably not going to do it. This concentration for B, which is 2nd order, and our value of K that we just calculated, and figure out what this rate would be. And so what I'm going to do when I get to this slide is I'm going to go back to the equation, solve for rate. So rate is equal to 0.577 over molarity times second, because that's what K is, and then times the concentration of B squared. And then in experiment 4, and again, my particular bias, I'm going to write it down twice, otherwise people will forget, to square either the number or the unit, 0.233 molar, and if that bugs you that there's nothing down there, put a 1, and then 0.233 molar over 1, and then this has 3, and this has 3, and this has 3, and this cancels this, and you're in molarity per second, which is a great test, because anytime you're solving for rate, that's what your final unit should be on rate. And I get 0.0313 molarity per second. So that would be the rate for trial 4. Interesting, the following reaction mechanism has been proposed for the reaction. Provide 2 reasons why this reaction is acceptable. I really like this problem because here's the 2 things you got to know. Whenever you have a reaction mechanism, the overall, when you add up all the steps, you have to get the reaction. So in other words, when we're all done adding up all the steps, it has to add up to this. It has to add up to this. And the stoichiometry on the slow step has to match the rate law. That's the 2 things that you look for. So if I add these 2 together, you can see that E would cancel E, 1B would cancel 1B. And so if you add these all together, you would get, on this side, putting them in alphabetical order, A plus B goes to C plus D. So the first reason is adding the individual steps. Probably a better term now that I think about it is the elementary steps together results in the equation for the reaction. And then I'm going to grab this eraser. And then 2, now remember, a lot of times people, the stoichiometry of the overall reaction is not what the rate law is. The rate law comes from the stoichiometry of the slowest step. And so if you look here, this is the slow step. And another way to write B plus B, they wrote it like this on the AP exam so you could see that it canceled. But another way to write that is 2B goes to E plus D. And so the rate law comes off the stoichiometry from the slow step. Now notice the slow step doesn't have A in it, so A is not in the rate law. And so the second reason is the rate law matches the stoichiometry of the slowest step. So in other words, this is what this reaction mechanism tells me, that the rate law would be some k, which we know is 0.577, but who cares, times the concentration of B squared. And there's no A in the slow step, and so there's no A in the rate law. And that's why that is a good reaction mechanism. And then finally, the last question, is E a catalyst or an intermediate? Because we know that A and B are the reactants and C and D are the products. So E has to be a catalyst or an intermediate. And the question is it an intermediate or a catalyst? So I would say E is an intermediate. And just to review that quickly, we know that catalysts are there in the beginning, which means they are on the left-hand side of the very first step. But the definition of the word intermediate means middle, and because E is generated in the middle of the reaction, and is consumed in a later step. The other thing I'd like to say is that, or you could say E can't be a catalyst because catalysts are there in the beginning, and it wasn't there in the beginning. However you want to see that, I think that's a pretty easy problem. So I'm going to stop.